So, in the brain research part, it's going to take, about 12 minutes, just to let you know, get your brain prepared. But at the end of the 12 minutes, I'm going to ask you to share one thing with your partner that impacted you. So as you're kind of listening to this, and hopefully you're engaged and you're not just a passive listener, but you're really trying to think and comprehend, and inside your brain you're kind of connecting what I'm saying with what you already know. And at some moment, as you're doing that, something may happen and you go, oh. Or you may go, or you may go, huh? Whatever the thing is, at that moment, just jot it down. Maybe you'll jot down, a quick something, so at the end of the 12 minutes, you'll remember to share it. So, that thing may be, you may be surprised, you may disagree, you may have an experience, you may go, oh yeah, that just happened to me today in my class. Or just anything. I don't mean to limit you in what you might be wanting to share. Anything you find worthy of sharing. So here it goes. Put your seatbelts on, it's going to go fast. Over the last several years, I've read a whole bunch of books about brain research, as Linda and I talk about often. Is this brain research thing is really fascinating. And so I've kind of just consumed all I can consume about it. And in this particular case, Brian Butterworth wrote a book called What Counts? And he says, all possess a fundamental number sense, which he calls numerosity. You know when people say, well, I'm just not good at math. I don't think that's true. The brain research doesn't support that. Now, they may not be good at what we're trying to get them to do in the traditional curriculum, but this idea that I'm just not good at math and some people are good at math isn't really true according to the research. This inherent ability is even more basic to human nature than language is. You ever hear anybody go, well, I'm just not that good at reading? They don't say that, do they? But they're proud to say they're not that good at math. But that's really not what the brain research would suggest. In fact, the inherent ability to do mathematics, to at least have some number sense, is more fundamental than language. Numbers do not exist inside our heads the way words do, however. It's not the same thing, language and numbers. But there are some kind of intelligence with their own brain module, and that module happens to be your left parietal lobe. That is where math happens. Now, you want to see your left parietal lobe? Here it comes, here it comes. No. There's your left parietal. That's where the math happens. Now, unless there's been trauma, unless there's injury, unless there's something physically wrong or anatomically wrong, that's where the math happens, and all have the fundamental ability to have that number sense right there contained in that left parietal lobe. Keith Devlin, he's on NPR, he's the math guy on NPR, often if you ever listen to NPR, and he says, in this Math Gene book, he says the ability to think mathematically arose out of the same symbol manipulating ability that was crucial to the first emergence of true language. So there is a similar path, as Brian Butterworth might say, but they're not the same, but there's a similar path of development between the two. And we should be able to do math, whatever that means, we can talk about what that means later, as well as we speak. But we don't often recognize when we are using mathematical reasoning. In fact, later on I will argue that adults do not necessarily, when they're engaged in doing math, it's not the same math they experience in our classrooms. They adapt and they figure out their own way to do the math they need to do, and it's not necessarily what we taught them. But they all have that ability, they all have the ability to do math as well as they speak sometimes, and they just don't know it, because it doesn't feel like what they've experienced in the classroom.
So the parents are right, there is a math gene?
No. When we get into this whole brain research world, there is sort of the real science of the brain research, but then there's also then people writing books about what does that mean in terms of teaching and learning. And this particular book, How People Learn, Brain Mind Experience in School, is just sort of a general how people learn. And they would say, bring students' ideas about how to solve or analyze problems into the public forum of the classroom. Bring students' ideas. Now, I don't know about you, but in my teaching, it's not always that I allow that to happen. And that whole brain research and that whole idea that everybody has the fundamental ability, we all have that left parietal lobe, but yet we kind of squash it. And we don't allow students' ideas to bubble up. We tell them what their ideas should be. And so they say, how people learn, that's really not the best way. We should allow student ideas to emerge in the classroom, become public. Allow students to decide whether something was mathematically reasonable. How about this one? Your students are working and you come by and, is this right? Is this right? Who's the only person in the room who can tell them it's right? you. And I say, no. I try to do my poker face. I don't have a good one, but I try hard. How should they decide? The correctness of their work should reside within the mathematics itself. Does it make sense? Is it reasonable? Whether it's right or not, their thinking, their ideas, their solution should not be because I say so, or the back of the book says so, or whoever says so. It ought to come from them, their own thinking. We should focus on mathematical meaning. Everything should have based on meaning. The meaning of multiplication, the meaning of the derivative. I have to tell you one. The meaning of average. Some of you who have been in my workshops know I like to talk about average a lot because people don't really know what average means. They know how to get it. They know how to add up the numbers and divide by how many numbers there are, but they don't know what average really means. And so yesterday, 2 days ago, a colleague from SCC sent me a link to this video. You know, one of those places where you can watch videos about people teaching math. And there's this guy teaching about average, and he says, so the average is just sort of a representation of all the numbers. What the heck? What does that even mean? So then he shows you how to do it. Oh yeah, and the answer is 7.5. And 7.5 just kind of represents all the numbers. Could you be more vague? Could you be more unmeaningful to really make sense of an idea? And so, wow, that just really hits me hard that we need to focus on meaning, everything that we teach. And when ideas or strategies for solving problems come up, bang, we got to discuss those things. You know, students don't just somehow magically learn how to solve problems. When those ideas come up, when they're sharing in the public forum and somebody has a good idea for sharing, or for strategizing a word problem, we need to bring that up and discuss it and make it a major part of our teaching. That same organization came out then with a specialized How Students Learn book just for mathematics in the classroom. I like that one much better. The other book, they had a whole chapter on like social studies. I skipped it. Although Brad, the chapter on chemistry, I read very carefully. Anyway, in this book they say, in terms of how students learn and some of the issues related to it, here's a big one. We must engage students' preconceptions and their often misconceptions. Let me give you some of them. Students will think, math is about learning to compute. Now think about, especially if you're doing the pre-calc and the calculus and so on, and we're really focusing on ideas and making sense and all that. The computational part is like that of doing mathematics. That's just a part of the big puzzle called mathematics. But how many of you have experiences like me? You go out to dinner with some friends, the bill comes, oh Scott, you figured out, you split it up, you're a math teacher. I'm like, I can't just
I say, heck
compute.
yeah, find those for free.
Yeah, exactly. But the point is, they think, the general public and our students think, that math is about computation and that's all. It is so much more. We need to address that up front and help people to know that that's not all that mathematics is. Students might think math is about following rules that guarantee right answers. And that's, you just got to figure out you just have to enact the right rule at the right time and you'll get the right answer. And if I could just do that, the good students can and the bad students can't do that. That's not what math is about. Math shouldn't be about just memorizing the right procedure at the right time. Some people can do math, some people can't. You've heard that one, right? How many times have you been at a parent-teacher conference and Johnny's got a D, and mom and dad go, well, yeah, I wasn't good at math either. And the brain research just doesn't support that. It just can't be. We need to address that preconception, misconception, and do something about it. In fact, this book goes on to say, understanding, if you really want to understand, it requires some factual knowledge, sure, but it also requires conceptual frameworks. You're going to see some of that today. We must build conceptual understanding, procedural fluency connected to that conceptual understanding, and no, we just connect it all. Not that there isn't procedures, not that there are not computations within mathematics, there are. But it has to be connected to conceptual understanding, otherwise it's just like mindless stuff that they're doing. And then we want to build in our students, I hope, is resourceful, self-regulating problem solvers. I don't know, did you watch any of the news, you know? Do you think we have any resourceful, self-regulating problem solvers running our country? Sometimes I wonder. There's another book, Marcia Tate, Mathematics worksheets don't grow dendrites.